So the title of the talk, which I was just a bit too lazy to write, is Suppressing Variance in Cosmological Simulations, or How I Learned to Stop Worrying and Love the Zadovich Approximation, which is a reference to a really great movie that you should all watch. So this talk is split up into 3 parts because I want to first motivate the problem, then I want to motivate how we could try to solve this problem, and then I will actually sort of go into a little bit of technical detail of how I do this calculation. This is very similar in theme and in spirit to the talk that I gave on Monday, because it basically, involves n-body simulations, and then at the end of the day also involves the use of actually quite technical perturbation theory to solve a problem in the realm of n-body simulations. This is based on...
Excuse me, can I ask for a favor?
Yes.
It's very hard to read what you wrote.
Ooh. I can try to...
Your writing is a bit too small for that.
Okay, I can try to make it
somewhat bigger, okay?
Okay.
Or maybe they can focus the camera closer, I don't know. Okay, either way. Thank you.
Tá focando em mim, não na lousa. Não.
Mas ela tá na lousa. Eu posso dar mais um. Eu vou dar mais um.
Yeah, so this talk is based on 2 papers and 1 in preparation that I'm writing right now with a gang of collaborators that I've been working with for quite a while now. So this is Stephen Chen, who's also a postdoc at the Institute with me. Well, actually, he just left the Institute. Martin White, who's a professor at Berkeley, and Joe DeRose, who's my academic older brother. And so 2 of these papers are out. One of them I really hope will be out next month, which is why it has this auspicious archive listing. But yeah, so the point of this is that this talk is split into 3 parts. So I'm going to tell you a little bit about n-body simulations in large-scale structure, which I mentioned a lot before during the actual colloquium. And I specifically want to motivate this issue of sample variance or cosmic variance, which you may or may not have heard of, but it's kind of an issue that you always run into when you try to use simulations in cosmology. I'm actually going to switch gears and go strictly into the realm of statistics. So I'm going to set up an optimization problem that in statistics, in the theory of Monte Carlo, is known as the method of control variates, and just show some very simple properties about this optimization problem, but which seem very enticing and powerful. And then I'm going to talk about this Zadovich approximation, which is a model for the formation of structures in the universe as this control variate. So for this question of the cosmological n-body simulations, I showed videos during my talk where you had particles that were moving in an expanding universe, but in a frame that was co-moving with the expansion. So this looked like a drag force, and they were just interacting and attracting gravitationally and moving towards each other. And I mentioned that there was some randomness in these initial conditions, and you can kind of start to understand why if you think, or in these simulations, which you can start to understand why if you think about how are you going to initialize this simulation. So if I were to just take a patch of the universe, this is a cube in theory with size L, and I just randomly placed particles inside this universe and evolved them, well, they would just sort of evolve in a kind of not very interesting way. It's actually sort of a problem in plasma physics. It's a gas of ions, in this case of attractive ions, not repelling. So what we do in cosmology is what we try to impose those density perturbations really at the beginning of the universe that I showed that look like the statistics of the cosmic microwave background. We want to imprint the distribution of particles in the simulation with those density perturbations. So I had mentioned, right, that there were basically fractional density fluctuations at the very early universe, which I defined as the density at a given point minus the average density of the universe. And Eduardo, let me know if this is bigger and better. If not, I can go even larger.
For this blackboard, this is fine. The other blackboard is more complicated.
Okay. And so we have this. And so one thing that you could imagine doing is, for example, saying, okay, I want to simulate a patch of the universe. Maybe let's say I want to simulate a representative patch of the universe, which is like 3 billion light years across, so 1 gigaparsec. So let's say that this is about 1 gigaparsec. Then what you're simulating is actually a very large amount of mass that you're going to have to distribute into these particles, into these constituents. And so just as a scaling calculation to have some sense, right, the total mass contained in this patch of the universe is going to be something like rho bar times the volume, which is L cubed, which gives you something like omega matter, which is the amount of dark matter in the universe today, times 7 times 10 to the 10 solar masses. Oh, sorry, this is for, yeah, so sorry. If this is 1 megaparsec, if this were a small patch of the universe, so about 1/1000th of this, and this had, yeah, so this would be about 10 to the 10 solar masses. Sorry, I forgot to write this down. In about 1 cubic gigaparsec of the 1 cubic megaparsec of the universe. But what you could imagine doing is basically saying, well, I want to place particles according to these anisotropies. And so I could maybe say I have a density field that I'm going to split up into several sort of small patches. Each of these is going to actually inherit a fractional overdensity of size delta relative to the mean. And then I will just place particles according to actually not the average density, but particles such that they add up to the total mass density here. And I can just place them randomly inside, maybe. And this is a valid way to set up cosmological initial conditions for the universe. It's not really what we do, but what you're going to get is basically a few more particles here where the universe was overdense, a fewer particles here, and then you could just evolve them according to a force law. And all that this is a very simple problem. The dark matter is not interacting. And so all that is happening is that these particles are feeling Newton's law. Really F equals ma, but in an expanding universe. And so what you can write in these coordinates that are co-moving, where the frame is expanding with the universe. And so if I have a co-moving position for a particle, x, in a suitable unit of time, which I'll mention in a second, every particle that I'm tracking its position is just actually going to feel a force law that is nothing more than F equals ma, but with a friction term because of the expansion of the universe. And you could run this forward, and you would get an n-body simulation. So if you ran it backwards, so this is a little bit tricky, actually, because this is a second-order differential equation. So there are two solutions in principle. This initial condition here is normally what people normally set as the growing mode to the solution, and there should be a decaying mode. But if you run it backwards without it, then you miss that contribution from the decaying mode. Yeah, so in the linear theory, when you linearize the fluid equations, and you look at the evolution of the density perturbations in linear theory, you get something that looks like this, which is also a second-order equation. It's just a wave equation. So you're going to get two solutions. One where the amplitude of the solution grows as a function of time, and one where it decays as a function of time. So if you run it, if you initialize your simulation with only one of the modes, and people normally only run them forward, so they only initialize with the growing solution. It doesn't matter what solution well, we see the growing one today because the decaying one is going to have fallen off unless you set it to some arbitrarily extremely large value in the future, or in the past, which would have been ruled out by the CMB. Yeah, exactly. Sorry. So we're just going to basically be tracking a force law like this. But this matter density field here, which I used to sample the initial conditions for my simulation, is one draw from a random distribution. And it's actually a Gaussian, or to very good approximation, a Gaussian. And so really what you actually do in practice is you go to Fourier space, so you write the Fourier transform of whatever this field is. And what you essentially do is you say that this is going to be sampled, each Fourier wave number is going to be sampled as some normal contribution with mean 0 and with a standard deviation which goes as the power spectrum of your initial conditions, which are these cosmological initial conditions that you derive from something like a Boltzmann code. There's also some scalings here, so you technically have to divide by the volume for this to be dimensionless. It's the volume of the fundamental cell over 2. And there is an equivalent imaginary component which looks the same. And so what this means is that there is some randomness imprinted at the start in your simulation. There is some variance, which is the cosmological variance, but you're running this on a universe of a finite amount of size, and you just have one single universe. And so this can actually affect what you measure from the simulation. And so just as an example, what people might be interested in doing is measuring the power spectrum of the simulation. So say they've evolved this density field. The force is just basically the 1/r² force that you're feeling from every particle around you. Say you evolved this to something at very late times, and you want to measure the power spectrum. So I had mentioned in my other talk that, let me keep notation the same. So for two Fourier modes in a continuous distribution, or sorry, in a universe of infinite size where everything is continuous, I basically get something that looks like this. Where this is not necessarily the same power spectrum that I put into the initial conditions. When you go to a discrete universe with a finite size in a simulation, basically your delta function will collapse into something that looks like this. And this is just a Kronecker delta for the discrete Fourier modes that you get because you put the system in a finite volume, and so you've discretized all of the momenta in it. And so really what you get is that if you take the equivalent correlation function but in a box, you get something that looks like, and so for the discretized modes, I'm just going to have them be sitting down here instead of being a continuous argument. Something that looks like the volume of my simulation times this delta function times my power spectrum evaluated at the absolute number, at the absolute value of this wave number. And so if you wanted to estimate what this function is, and you have a discrete collection of modes, what you could do is basically just replace this expectation value by an average. The average is an unbiased, so the sample mean is an unbiased estimator of the expectation value. And so when you try to measure the power spectrum in a box, you basically get something that looks like 1 over a variable called nk, which I'll define in a second, divided by the volume of the simulation, where all of these k's now basically exist in some finite bin. And so as a representation, what you're basically doing is, if you're looking at all of the different wave numbers that you have access to, and so for example, this is just 0, this is kx times the length of your box over 2 pi. And this is 1, 2, 3, 4. Depending on the wave number that you're trying to measure, what you're basically defining is some shell, and you're counting how many modes actually fit into this shell. And so this is what defines the number of samples that go into your sample mean. And this factor of volume shows up because I discretized this delta function that shows up over here. Okay, so what this is basically the estimator for a 2-point function, or for this power spectrum, in a box that has a finite volume and that I've discretized the whole system. Yes, but nk is not, nk is actually fixed by the constraints of the simulation that you're running. So that's the second part, basically. So basically, what you can imagine nk as being is what is the volume of this shell that I drew in 2D relative to the fundamental volume of my Fourier domain over here. And so what you actually get is that this number of Fourier modes looks like k squared delta k, which is essentially just the volume of that. So delta k is the thickness that I assumed, which is a free parameter in my measurement, times the volume of the simulation over just a factor of 2 pi squared related to the geometry. And so it's sort of a textbook calculation to then try to figure out, if this is an unbiased estimator, which is somewhat easy to show, what is the variance of this estimator? And so basically, if you compute this quantity, what you end up getting is something that is proportional to your theory expectation for the power spectrum squared divided by k squared delta k times the volume. And so more specifically, the fractional error with which you measure the power spectrum, so your delta P or sigma P over P, goes as 2 over nk. So this is kind of interesting. If you make your volume bigger for your simulation, then the variance gets smaller. But also, since you have a finite size and your Fourier domain has a finite size as a result, so your fundamental cell is fixed, as you go to very low k, there just aren't that many modes that actually contribute to the sample mean. And so what this means is that as k goes to 0, your measurements are noisier and noisier and noisier and noisier. And so just as an illustrative number, basically if you have a box that is 1,000 megaparsecs on the side, and you're trying to measure a Fourier wave number of 10 to the minus 2, k, of 1 over megaparsec, this is a 40% error. This is 0.4. You have a 40% error on the measurements that you're making. And this is for the power spectrum. This gets even worse if you try to go to, for example, a 3-point function or something like that. And so you could say, oh, that's okay. I will just make my box size bigger. But as you make your box size bigger, you're having to put more and more mass into the universe, which means you're having to either make your particles represent a larger and larger chunk of the universe to keep the resolution fixed, or the resolution blows up, and your small scales will be completely wrong in your simulation. So there's this sort of tightrope between making my box size big enough that I can actually measure things in it, but also making sure that I have enough particles that I'm resolving all of the high K modes in this box. Yeah, so normally what people assume is something like, actually 1 megaparsec, so it's about 10 to the 10 solar masses is about the size of one particle in an n-body simulation. No. This is a dark matter particle. So something like the Milky Way has 10 to the 12 solar masses in total, right? So that's about 100 particles is one galaxy. Well, it depends. This is for cosmological things. So if you want to go into the galaxy formation realm, then it gets worse. But yeah, this is a big problem. Like, this is actually kind of an issue. Something like that. So normally for a dark matter halo, it is considered relatively well resolved if there's 100 particles in it. So yeah. So for this simulation, which has 1 megaparsec grid size, and if I were to put it in a gigaparsec volume, which is roughly what these Quixote simulations from Paco used, you would get something like 10 to the 12 as your minimum halo mass, at least. Not for this. But so for example, illustrious TNG is 250 megaparsecs total, but they discretize this grid into something like 6,192 individual cells. So their fundamental particle size is significantly smaller, so it's something like 10 to the 6, I think. So for a real hydrodynamical simulation, then you would basically have to go to an extreme resolution, which is part of the problem. Because in illustrious TNG, this is so small, you cannot measure anything of large-scale quantities. So this is actually a problem. Like when you try to do very accurate modeling, which was the whole point of my talk yesterday, and you're trying to rely on simulations, this fundamental noise is just killing you. And so what you could imagine doing is just, well, let me run 2 simulations or 3 simulations or 4 and just average them together. But this is really low convergence, right? Because all that this means is that for n simulations, basically whatever uncertainty you had on what you were measuring, this will just go to square root or to 1 over n. So you just get root n convergence, which is actually quite slow. And one of these supercomputer simulations takes about 10 to the 4 CPU hours, so about 10,000 hours on a CPU, just for reference. This is so hopefully you're slightly convinced that this is a little bit of a problem at least. And so the question is, can we do better? Because this noise, we actually put it in by hand. Whatever this noise is, I put it in by hand when I chose to sample random initial conditions. Which, to be fair, that is what the universe's initial conditions are, so we have a reason for doing this. And the answer is actually yes. And the answer actually goes back to something that if you just open textbooks in statistics, it's just there in chapters. And it's this thing which are called control variates. And so the idea is, I just described that I have some quantity that I want to measure at very high precision, this power spectrum, whatever it is, but it's very expensive to run. So I'm going to call this x hat. A hat always means it's an estimate from some random process. And all that I'm going to do is define a new quantity, y hat, which is a linear combination between my very expensive simulation, a number that is just a Lagrange multiplier that I'll leave here right now, something called c hat, which is a very cheap simulation, something that does not take 10,000 hours on my computer to run, and its mean. This estimator is an unbiased estimator of whatever it is that you were trying to measure. And this is actually, sort of trivial, because if you take an expectation value, you're going to get the expectation value of x, but then the expectation value of c is this mu c that I just defined. So it is unbiased. However, what you can also do is you can compute the variance of this quantity. And what you basically find is that, sorry? Oh, sorry, thanks. And so what you basically, I wrote it right over there, so I do know what I'm talking about. But yeah, and so what you basically find is the following expression, which depends now on the value of this Lagrange multiplier. So this is going to be beta squared, sigma c squared. The covariance between x hat and c hat, plus the variance of my original quantity, which, for example, is that cosmic variance term that I had written down. And what you can then do is just take a derivative of this with respect to beta and set it to 0. And so if you set beta to be your original covariance between these two things, divided by its variance, then this actually implies that the variance of your new estimator is the variance of your old quantity times 1 minus and this quantity here is just my cross-correlation coefficient. So this is just going to be and so if I have a really cheap simulation that is somehow really correlated with whatever my really expensive simulation is, then I can parametrically cancel the variance in any observable that I measure from it, just by defining this linear combination between whatever I measured in my cheap simulation and my expensive simulation. Like, this is literally, high school algebra, and you can see that it works out like this. And this actually turns out to be really, really, really powerful if you can engineer and find the right version of what c hat is. Another way that I'm going to write this is what I might call the improvement from applying this method, or the effective number of equivalent number of simulations that I would have had to have run to cancel the variance to the same amount, which is just the inverse of this quantity, right? So it's just the noise of the original simulation divided by the noise of my reduced simulation. And so, if this is, for example, I thought I had a number here just for motivation. If this is like 75%, for example, the correlation, then the resulting variance that you get is 40% of the original one. So it's like you increased you ran 2.5 simulations together for free. So this is a really powerful technique, it turns out. But you have to be very careful when you set it up. And as an example, suppose that you had run, as your cheap simulation, the same exact code, but with settings that weren't as precise. Okay? But then that means, for this c hat, which is this control variate, that now when I try to measure its mean, I don't know what it is, because it's also from some random process, some random draw. And so if you basically do not know the mean very well, and you have to estimate it from some other sampling process, what this means is that the error bar increases in accordance by a factor that looks like this. And you can already sort of start to see that the same root n curse that plagued us before comes back. And not only that, you can then say, okay, when is this, my new error comparable to the error on the estimate of the mean of my control variate? And what you can basically find is that they're comparable to each other when, depending on how correlated they are to this factor here. But if you are in a regime of high correlation, rho is going to be close to 1. So this looks as 1 over rho squared. Sorry, so this is the number of C simulations, of cheap simulations that you would have to run to not ruin your method. And you can actually see this is exactly the same factor that I had derived before as the improvement. And so you actually didn't really gain that much. You still have to run n of the cheap simulations, which don't necessarily have to be that cheap, to make sure that this theoretical uncertainty is under control. Oh, sorry. And this actually happened in the real world. So there's this paper that the Dark Energy Spectroscopic Instrument wrote, trying to apply this technique to their flagship simulations. And because they used cheap simulations from this code called FastPM to measure their control variate, they had to run like 500 of them and average them to make sure that this error didn't dominate. And this ended up costing them 2.4 times 10 to the 7 CPU hours. For reference, 1 CPU hour on a national supercomputing facility is something like 0. Oh, this is really hard to write. And so you can see how much it cost them because they chose this inappropriately. And so really the name of the game for this method to work is you need to find something whose mean you can actually calculate analytically. And it does turn out that such a thing exists. Sorry, my watch is annoying me. Okay. And so there is such a model where this exists, where you can calculate this mean analytically, and it's a model of perturbation theory in large-scale structure. And so to see this, let's go back to that equation of motion that I had written down before for what a particle is doing. And I'll define eta in a second because I realized that I omitted it before. So eta is just my time variable. It's what we call conformal time. And so it's just in the metric you have ADT showing up, and you're just going to call this d eta to just pull everything out and make it look like a conformally flat metric. But nothing really changes. So all that this is saying is it's tracking something about the positions of the particles as a function of time. And so let me imagine I have some particle at some position q, that its initial position, let's call it its Lagrangian position. It's going to move around, end up somewhere else in the simulation, at its final position x, which is what we're trying to track at every time step. And so what I can do is just define a vector known as its displacement, which is effectively unique for every particle. This is a caveat, but let's assume that it is, which simply maps for every particle, if you tell me where it was in the initial conditions, where it will end up. It's strictly a function of this. This is actually a really interesting way to look at this problem, because in the initial conditions, I can assume that things were really, really, really close to uniform. And so I can write that in any volume element of the universe, I had this much mass contained within it, which is the average density of the universe times the size of this Lagrangian volume element. And from mass conservation, this has to go to some region which will now look like rho of x, d3x in my late time coordinates as I run my simulation. This just looks like rho bar times 1 plus delta x, d3x. And so what you can actually actually see is that when you write things down in this version of every particle has an initial position and gets reassigned somewhere, I can immediately write down what the density field is as just this Jacobian element, just this change from this mapping between the initial conditions and the late time conditions. And so what I find is that I can always just actually interchangeably write the dark matter over the density contrast field as the determinant of the Jacobian between this x coordinate and this y coordinate, which is a very simple partial derivative to evaluate. It looks like this. Okay? This mapping is not necessarily unique, so it blows up when this is singular, which happens when you have two streams that cross. So this is a thing to keep in mind, but let's assume that this doesn't happen for now. So this is known as shell crossing in structure formation. I can also rewrite this in a way that will turn out to be very useful. Just using some identities about how the Dirac delta function works, you can show that this is equivalent to writing the density field as an integral over all of the initial positions of particles over this initial Lagrangian space, and this mapping between the initial position and the late position with this displacement vector. So I kind of cheated in that I assumed it's easier to go from this to this, but it's an equivalency, so it works in either way. And then you can also take the Fourier transform of this to find an interesting expression, which is that the matter density field can actually be written at late times in a completely non-perturbative way as a function of only this displacement vector at early times. And so if I could derive equations of motion for psi, and I could figure out how to relate this to my initial Gaussian conditions, I immediately have this equation, which is non-perturbative and exact, to tell me how to remap this density field into the late time density field that I had written down. And so the way that you do this ends up entering what's called the realm of what's called Lagrangian perturbation theory. In practice, I'm not going to go over this, but the way that you would do this is we have the equation of motion for this x vector. We will simply, so this is like this. I would simply substitute in this expression here and try to find an equation for the displacements themselves. And so the equation that you end up finding is actually very, very nonlinear, and it's kind of a bear to solve, but I'll just write it down in case you're interested. So you basically start picking up terms that look like this Jacobian matrix between the two coordinates. You get some determinants and not just the matrix itself. Where this term over here is actually the Poisson equation. So what I'm actually really doing is taking a divergence of this equation here to get a scalar equation. And so this will bring a Laplacian of phi. So this term here is just the Poisson contribution, which is linear in the density field, but ends up depending on this Jacobian like this. So if you sort of stare at this a little bit, it's actually kind of a bear, because you not only have these Jacobian determinants, which are really nonlinear functions of your displacement, you also have these matrix inversions, but we can't compute this. And so there's a whole community and a whole art to figuring out ways to solve this equation in a perturbative sense, which goes under the name of LPT. But I'm just going to write the solution to the linearized version of this problem. And it turns out that the linear solution to this problem is interesting in that it only depends on the growth factor. So this is just the linear growth factor for the densities themselves that you get in normal cosmology, times whatever your initial density field was. normalized to some value. So whatever your realization for your simulation was, for example, that is just going to dictate the direction, and the amplitude and the time dependence only comes from this growth factor. So in this linear solution, all of the modes just evolve independently to each other. And so what this also means is that if I go back to this particle representation, I can Fourier transform this. Again, this eta is decoupled, so it'll just fall out. And so what actually happens to every particle in the universe is from its initial position, it gets a kick in some direction that is set by the local forces that it's feeling. So I'll call this the initial kick times this. And so in this picture, particles, instead of doing some complicated motion and being deflected and accelerated and so on and so forth, they just move in straight lines. Particles just move straight and nothing happens. So this approximation, this linear solution to this problem, is what Zodovich derived in 1970 and is nowadays called the Zodovich approximation. And I know it sounds stupidly simple, but there's a lot of really beautiful theory that comes out of this. So there's one paper which is worth highlighting, which is Shundaran and Zodovich, 1989, where they actually point out that this looks a lot like some problems in geometric optics of refraction through turbulent media. And so they point out that the problem of structure formation can be thought of as basically you have some ingoing plane wave and then some corrugated lens, which is the initial density perturbation, and things just get refracted and scatter and go off in different directions. And what time evolution is telling you is that at any given point, you're just looking at the projection of these rays on some screen as it moves. And this is exactly the same picture as why you get caustics at the bottom of a swimming pool, for example. And the cosmic web looks a lot like those caustics. If I had slides, I would show you a picture. I can show you after the talk also. And so this paper goes into a lot more depth with this analogy, and it's actually really beautiful. Yes, so this approximation breaks down during shell crossing, but there's nothing that prevents you from having shell crossing happen. Because in this picture here, you know what every initial guy was. As long as you just keep moving them along, they'll shell cross and move past each other. In the real universe, of course, things shell cross and then deflect and can, for example, form some bound object. Really, as they get closer and closer to shell crossing, they'll accelerate towards each other, and then you'll get some complicated dynamics. So yeah, but this is really interesting, right? This is a linear solution for the displacement from this equation. But if I plug in this linear solution into this expression here, this is an extremely nonlinear version of the density field. And this is why it produces the cosmic web and produces these caustic structures and all of this, very rich phenomenology. Because it turns out what the Zodovich approximation is actually doing is in some sense figuring out a resummed version of the linear solution to the density perturbations. No, so delta does not have to be small, actually. What matters in this expansion is that the derivatives of delta are small.
But you are answering already.
Yeah, so really the expansion that ends up happening here is that you're assuming that the gradients of psi are small, so the derivatives are small, but so deltas can be small, but the psi's don't have to be. Okay? And this is actually part of the problem. So sometimes papers in large-scale structure talk about IR resummation. It's related to expanding in psi as what you think is a small variable when it's not. Okay. There's also something very interesting about this approximation, which is that I can just implement a grid of particles. I can sample what their displacement should be from that density field that I had generated from that random process. I can figure out what is the kick that they're going to get, and I can just move them. And it actually turns out that on a laptop, once you implement this, which takes maybe an afternoon, you can run this in minutes or seconds, depending on the size of your simulation. And so if you give the initial conditions for this density field the same initial conditions that you had from the expensive simulation that you wanted, this estimator that I just wrote down, the Zadovich approximation becomes a very powerful C hat. And so just for illustration, if you look at what the cross correlation is between the Zadovich approximation and the final simulation, so if I generate this density field by doing this one displacement versus running the full simulation, and so this power spectrum here is a function of k divided by the square root of the Zadovich power spectrum and the n-body power spectrum. And this is k, and this is 1, and this is 0.1, and this is 10 to the minus 2, and this is 1. All the way out to k of 1, this is still 75% correlated at late redshifts. Even though shell crossing has happened, even though this approximation should have broken down, the cross correlation is actually still extremely high between the two density fields. And if I just take the sort of density fields that seeded that simulation, so this delta IC, and compute the equivalent cross correlation coefficient, this basically decays exponentially. So like I said, if you now have a theory or some approximate version of large-scale structure, which is 75% correlated with the final result. And so all that remains is to calculate the power spectrum of this quantity if we can, instead of running, even if it's a simulation on a laptop, running 10,000 of them is kind of a bore. I wouldn't want to do that. I would rather just do some math. Yes. So for people on Zoom, if they didn't hear it, they asked if their initial conditions were the same, and yes. So you're always matching the phases. Whatever random number generator you used, you put the same one in your n-body simulation and in your Zadovich simulation. Okay, so now we really need to compute this mean of whatever this quantity is. And this is where the Zadovich approximation, I think, really shines. So I'm going to use this equation here, but I guess I can go back here. Great. So I can just take this equation, and I can compute what the power spectrum of whatever this is. And the way that I do this is I'm just going to take and just plug in two versions of this field. So psi underscore 1 and psi underscore 2 are just psi at Q1 and at Q2. And you can show, if you rewrite this in a set of coordinates where you have the relative, so Q1 minus Q2 and Q2 plus Q2, that one of these integrals here, one of them will become a delta function. And so this is just translation invariance. And the other one is an integral that looks like this. And I've defined this vector of the relative displacements, which is psi of Q2 minus psi of Q1. Okay? So I just wrote a version of the fully resummed nonlinear power spectrum in terms of this correlation function here, which is kind of a tricky correlation function because it's really the expectation value of some exponential. But, yes. And you can show that it is in this decomposition here, basically.
He said yes.
Yeah, and also one thing just to mention is that there's also a term, so there's this -1, which causes a 0 lag term that I dropped in this expression. That it's only valid at k equals 0, but we don't care about k equals 0. So yeah, so maybe this is kind of a scary thing because this, you know, I mean, it's kind of a nasty term. But in the Zadovich approximation, what do I have? I have that this is my displacement, which is what shows up in that exponential. And this is the linear displacement, which is the Zadovich one. And this is the linear Gaussian density field. So really, this is actually not a scary expression at all, because this is just the exponential of a Gaussian random variable, or a variable that's log normal, or whose log is normal. And so what you can actually do is just resum this term here using the cumulant expansion. You could also Taylor expand this and compute the correlation functions of the individual terms, but now you're expanding in large displacements, and this is not good. But if you do this, you recover standard perturbation theory. So you can just do this cumulant decomposition. Where what I now get is that whatever the expectation value of the exponential of my random variable is, this is actually the exponential of the sum of the connected moments that I had, or the cumulants. And for a Gaussian, there's only n equals 2. This sum truncates. And so really what you get is that this e to the I k times delta is actually just e to the -1/2 ki kj, and all that I have is one correlation function over here, which is the correlation between these two displacement differences. And this guy over here, you can also write down. It's not too complicated. One problem with LPT is that Q is now a Lagrangian coordinate, where people normally assume Q to be a momentum. So, and you go back and forth between configuration and momentum all the time. So P is the inner loop momentum that I'm going to use for this. So all that I get is, oh, this isn't, okay. Yeah, I'll just do it here. No, I'll do it in the lower part. So this is something that looks like and this is the matter power spectrum, the linear matter power spectrum, the initial one. But just rescaled by the growth factor, right? So this will be d squared. This is, the rescaling is really simple. And so yeah, so in principle, I can just, whatever this thing is, I can plug it back into this expression here, and I can compute the Zadovich power spectrum exactly. For the sake of time, I'm not going to tell you much more, but we can do this, and we can evaluate this really rapidly numerically. You can basically write this integral over here in a form that is a very rapidly convergent series expansion of integrals over spherical Bessel functions, which you can turn into Hankel transforms, and then you compute it. And so in this first 2205 paper, we basically showed this proof of concept, and we used a Zadovich box and this prediction as a control variate and saw what would happen. And so the first thing is that you can actually get this version to match the lattice version of the perturbation theory to extremely high accuracy, so within 1%. You know, so that this mean that I had written down is not going to be unbiased. And then when you plot this improvement, I guess I can go over here. For the Zadovich approximation, the line kind of looks like this, where this is 10 to the minus 2, this is 10 to the 4. And out here at k of 1, this is 1, and at k of 0.1, this is about 100. So in the regime where it's the most expensive and most difficult for you to measure your n-body simulation, where your original accuracy was something like 40%, by using this technique, which you run on a laptop instead of running 100 supercomputer simulations, you get the equivalent of having run and averaged 10 to the 4 simulations, which is pretty good. And so the rest of the paper and the rest of our works were sort of concerned with extending this to not just the matter power spectrum, but to the power spectrum of biased tracers. So in my talk, I mentioned this notion of hybrid EFT, where in hybrid EFT, the building blocks were 2-point correlation functions of this expansion. So I wrote many things that looked like Pij, which was the correlation of two different operators that had to be measured from n-body simulations. You can also realize these operators in this Zadovich lattice scheme. And what we show in our paper is that you can also calculate them analytically. Because what you can basically show is that this is equivalent to, it's a very similar formulation to that problem. So you still have these displacements showing up, but it actually turns out that you also need to put the operators downstairs. And this complicates the expectation value a little bit, because it's not just this term purely anymore. You have these guys showing up downstairs. But what we basically show is that you can define a generating function. So where basically these are just all of the fields that show up in your perturbative bias expansion, all of the linear versions of the fields. And you can actually show that you can just take derivatives with respect to lambda. This will drop a field, and then you set lambda to 0, and you recover this expression. But here, since everything that I've written down is Gaussian, as soon as I can also actually just resum using the same cumulant theorem, and I can get the generating function in the Zadovich approximation exactly. So we also do this. There's like 10 different ones. We show in our paper that you actually need to compute the corresponding 2-point functions to sort of arbitrary to all loops, which we can do. It's actually not that difficult because it's Gaussian, it ends up truncating. But we do this for basically all of the 10 different generating functions of the theory. And we implement it, and we basically always get something that's about, it goes up to 10 to the 6 in terms of n equivalent. And this was actually really cool because I think people trying to build these emulators, these simulation-based schemes, were always limited by the accuracy because they couldn't run, you want to run a lot of simulations because you want to sample the cosmological parameter space, but then you can't really make them really big or else they become too expensive. And so what this lets you do is run significantly smaller simulations, but still get the accuracy to a very high level because you canceled the volume issue. So that Emulous Heft suite that I mentioned at my talk on Monday, we were basically able to run like 150 simulations because we were able to implement all of these techniques for and cancel the variance of every observable that we measured from it. Yes, so they enter, but notice that they have these like this is sort of like in QFT language, right? This is like the source and this is the current, and you take derivatives with respect to the current and then set it to 0. So basically, if you want so I can show you an example. If you want to compute what we would call the delta-delta correlation function, which is the linear bias version, then you would basically take one derivative with respect to Q1, one derivative with respect to, or lambda1, which is the one at Q1, one at Q2, and you basically show that, so this F is just what this is, so we called this Fij, and so this looks like, times this exponential term that ends up factoring out when you drop the currents to 0, right? Like, and we can compute this, and it works, basically. So I think this is actually really promising because a lot of what's been holding back simulation-based modeling are these issues of can you trust the noise that's in the simulations in the first place? So in the second paper, in this 2210 paper, we showed that you can also extend this to redshift space, because it turns out that in Lagrangian theory, the redshift space mapping is very simple. It's just adding a term that looks like a time derivative of this displacement originally. And this paper, this 2509.I hope that is coming out soon, is extending this to the 3-point function. And there are a lot of subtleties, and it actually turns out that the Zadovich approximation does not work as a control variant. It's not, the correlation coefficient is not 1, but I'm on time and it's kind of late, so I'm happy to tell you more offline. But yeah, I mean, hopefully you can actually see that, we started at simulations, we ended up doing some somewhat, technical LPT calculations, and we got significantly better simulation-based results as a result of that. So that's why I love the Zadovich approximation.
So people in Zoomland, you want to?
I have a quick question. So what justifies the use of this Gaussian approximation?
Mm-hmm.
Is there some sort of central limit theorem that is being assumed?
No, so actually the Gaussian approximation comes from, it's sort of one of the prediction, so there's two things. One is an empirical fact that the matter fluctuations at the CMB are very highly Gaussian because the temperature fluctuations of the CMB are very highly Gaussian. And we know that the CMB sets the initial conditions for the structure formation problem that I wrote down. The reason why the CMB is very highly Gaussian is related to the fact that in general, any theory of inflation will tend to produce, well, okay, not any, but theories of inflation that people enjoy these days tend to produce very Gaussian fluctuations. But again, that's because that's what we saw in the CMB. So there are small corrections, what people call primordial non-Gaussianities, that might change this story a little bit. But I've neglected them for the purpose of this talk.
But when structure is beginning to get formed, wouldn't you expect deviations from Gaussianity?
Absolutely. But this is why this approximation is so powerful. So the displacement, if you can see that I'm writing down over here, this displacement, as long as I'm using the linear solution is always Gaussian because it only depends on the initial conditions. And the structure is very non-Gaussian, but it's non-Gaussian in a way that I know because it's a resummation of a Gaussian random variable.
Yeah, sure. But, in field theory, this is called a vertex operator in a scalar field.
Okay. Would love to know more.
Right. And you use a well-known expression for that.
Okay.
In terms of propagator. Okay.
Mm-hmm.
Yes. Okay. Thank you. Another question is, where do you see all of this going, going forward in time? What is the future for all of this?
Yeah, for sure. So like I mentioned, all of this only lets you do simulation-based modeling for the 2-point function, but that's also where a lot of these surveys that I mentioned on Monday are sort of at. So this is only probing the dynamics. It's not probing, kinematics in the QFT sense because there's only 2 legs. It's really just a propagator. And if we want to analyze the 3-point function, then you're starting to understand how non-Gaussian structures evolve in the universe. This has complementary information on this growth of structures that is not captured in the 2-point function. But it's much more difficult to model. Simulations, it turns out, are much more important for anything that involves non-Gaussian contributions. And so this program, we solved it for the 2-point function. We have not solved it for all two-point functions. So the two-point functions of tensor operators, this is still something that I'm planning on working out. But going to the three-point function is actually going to help a lot because it's going to let us deploy models that are simulation-based to analyze data that are much more powerful than what we could get from naive perturbation theory. Because this scale that I had mentioned, this nonlinear scale, kills you for the three-point function much more quickly. On top of that, one of the results from this paper that I'm hoping to put out soon is that we actually show a way to extend this scheme to all endpoint functions. And in particular, what this means is that you can calculate the four-point function, in principle, from a simulation with a lot less noise. And a lot of people in this room have spent a lot of time trying to characterize the four-point function of structures because this also tells you what the variance of the two-point function is, because that's a four-point function. So, in simulations right now, people run suites of thousands to tens of thousands, in surveys, people will run 1,000 or 10,000 simulations to try to measure the variance of the two-point function empirically. But if you could have a way to just measure the four-point function directly in the equivalent kinematic configurations, at very high accuracy, you wouldn't have to do this. And so you would basically solve this problem of what people in cosmology call covariance matrix estimation. So I think this is, to me, kind of the holy grail of this, which is writing down a scheme where you can compute the four-point function in this resummation way and resummed way analytically.
Great, thank you.
Okay, if there are no more questions from Zoom, the audience here is a bit tired.
All right.
Okay, we can thank Nick again.
Thank you.
So what is a vertex operator in QFT?